Trigonometry starts with a sudden influx of overlapping identities, complex formulas, and abstract functions. Attempting to absorb these equations through rote memorization is unsustainable. The mental load required to track these shifting variables algebraically eventually leads to a breaking point. The right-angled triangles from Class 10 provided a solid start, but they are limited to static, fixed geometry. Calculus requires a model for continuous, periodic motion. A triangle cannot easily calculate the coordinates of a point that spins infinitely around an axis. To handle that motion, we have to look past individual triangles and focus on the geometry of a circle. The goal is to translate abstract rotations into a physical, geometric territory where you can see the answers instead of just calculating them. This is the unit circle. It functions as a spatial map designed to navigate infinite rotation. First, we have to change how we measure angles. The 360-degree system is an arbitrary convention. It doesn't relate to the actual dimensions of the circle, which makes it difficult to use in natural physics or calculus. A radian is a measurement based on the circle's own anatomy. If you take the radius and lay it flat along the curve of the circle, the angle it creates is exactly 1 radian. If you keep laying those radius lengths down, you'll find it takes just over 3 of them, exactly pi, to reach the halfway point of the circle. This gives us our conversion. 180 degrees is exactly pi radians. To convert any degree into this physical measurement, you multiply it by pi over 180. Working in radians is the standard for calculus because it links the angle of a turn directly to the distance traveled along the edge. Now we set the boundaries of the map. We use a circle with a radius of 1, centered on an xy coordinate plane. Every point on the edge of the circle has a coordinate. The horizontal distance from the center is the cosine, and the vertical height is the sine. As the radius rotates into the second quadrant, you can see the blue cosine line move to the left of the center, making it negative. The red sine line is still pointing up, so it stays positive. This pattern continues through the third and fourth quadrants. The signs of sine, cosine, and tangent change based strictly on which side of the x or y-axis they fall on. This is why the all-silver teacups rule works. It isn't a random acronym, it's a shorthand for the physical reality of the xy plane. Advanced identities like sum and difference, or double angles, are often treated as more things to memorize, but they are actually tools for restructuring equations. For example, the double angle identity for cosine allows you to express the same value in 3 different ways. Swapping between these forms is a tactical move. If you have a squared term that is making an equation impossible to solve, you can use these identities to rewrite the expression into a simpler, linear form. This ability to transform the structure of an equation is essential for integration. Many calculus problems are only solvable after you use an identity to change the math into a format the rules of calculus can actually handle. In earlier math, a problem like where does sine equal 1/2 ended at 30 degrees. There was one specific answer for one specific triangle. But on the unit circle, if you keep rotating past 360 degrees, you will eventually hit that same height again. Since you can spin around the circle forever, there are an infinite number of solutions. To write down every possible answer at once, we use the general solution. The n pi part of the formula tracks how many half-turns you've made around the circle, while the -1 to the power of n accounts for the way the sine value flips between positive and negative quadrants. By using n as a placeholder for any integer, the formula captures every future rotation. Whether you spin around the circle twice or 1,000,000 times, this single line of math stays locked on the correct coordinates. By defining the behavior of one rotation, you can now predict the output of any rotation. You have moved from solving for a single point to describing a periodic pattern that continues indefinitely. Let's test your spatial intuition. Locate the angle 7 pi over 6 on the map. Using the ASTC rule and the quadrants we've discussed, determine if the sign of that angle is positive or negative, and leave your answer in the comments.
For years, you've relied on 360 degrees to measure angles, but that number is a historical choice. Ancient civilizations simply preferred base 60 math. To perform calculus, we need a unit of measurement derived directly from the physical dimensions of the circle itself. If you take the radius of a circle, peel it off the center, and wrap it along the outside edge, That specific arc length creates an angle. That angle is exactly 1 radian. If you keep wrapping those radius lengths around the perimeter, it takes a little over 3 to complete a half circle. It takes exactly pi radians to reach 180 degrees. This gives us a mathematically permanent conversion baseline. We lock this structure onto the x and y axes of a coordinate plane, with the radius set to exactly 1 and centered at the origin. This is the unit circle. Any point on this circle's edge drops down to form a right triangle with the x-axis.
Because the hypotenuse is always 1, the square of the horizontal side plus the square of the vertical side must equal 1. This is how the Pythagorean theorem becomes our primary trigonometric identity. This architectural grid allows us to map and calculate complex mathematical positions with absolute precision, removing the need for geometric guesswork. The vertical y-coordinate is sine, and the horizontal x-coordinate is cosine. To track positive values through the quadrants, use all, silver, tea, cups. Sine stays positive in quadrants 1 and 2. Cosine stays positive in 1 and 4. To solve for an unknown, follow a 3-step process. Identify the quadrant, reduce to the reference triangle, and apply the algebraic identity. If given a sine value of 3/5 in quadrant 2, we can find the exact cosine. Look at the map before you touch the numbers. In quadrant 2, every x value is on the left side of 0. That means our final cosine value must be negative. Spatial awareness dictates the result before the arithmetic even begins. We drop data into the geometric anchor. Rearranging the identity to isolate cosine, we set up cosine squared x equals 1 minus 3/5 squared. Squaring 3/5 yields 9/25. It's 2 valid results, positive 4/5 and negative 4/5. Because we established the physical boundaries of quadrant 2 earlier, the ambiguity vanishes. The map dictates a negative x-axis, which overrules the raw numbers. The cosine of x is negative 4/5. This value locks directly into a physical coordinate. The exact position on the circle's edge is negative 4/5, 3/5. Mastering this rotational mapping serves as the foundation for modeling waves, oscillations, and physical cycles in higher-level sciences. This process relies on 3 rules. 1. Radians dictate physical length. 2. The ASTC grid governs the positive and negative signs. 3. The Pythagorean identity connects the exact coordinates.
Hit subscribe to simplify your syllabus. And turn on notifications so you never miss a splash.